everyone, welcome back. In this video, we will introduce another continuous distribution, the gamma distribution. Now, before I get too deep into this, I do want to let you know that I am recording in the middle of a morning thunderstorm, so if you hear any weird booms or pitter-patters coming through, that's where it's coming from. So let's get started. We'll start by defining the gamma distribution and talking about some properties of the gamma distribution. We will also in this video explore some special cases of the gamma distribution, namely our old friend, the exponential distribution and the chi-squared distribution. So we say that a random variable y follows a gamma distribution with two parameters, alpha and beta, if the density function looks like this. Little f of y is 1 over the gamma function evaluated at alpha times beta raised to the alpha power times y to the alpha minus 1 times e to the negative y over beta. Now let's talk a little bit about the gamma function if you haven't seen this before. The gamma function, capital gamma of alpha, or of some general value a, is evaluated like this. The gamma function is the integral from 0 to infinity of t raised to the a minus 1 power times e to the negative t dt. Now, there are some shortcuts associated with this gamma function. Specifically, the gamma function evaluated at alpha plus 1 is just alpha times the gamma function evaluated at alpha. For any integer value, the gamma function is alpha minus 1 factorial. So we have some shortcuts for working with this gamma function. It turns out that we'll rarely need to work with it directly. Most of the time we'll be able to use one of these two shortcuts to simplify the gamma function. So we say that this distribution y, or this random variable y, is distributed gamma with parameters alpha and beta. Let's take a look at what this gamma distribution looks like. Depending on what we set alpha and beta to be, we can have some pretty different shapes for this gamma distribution. So for example, a gamma distribution with alpha and beta both equal to 1, represented by this coral curve, looks a lot like the exponential distribution, just a trailing off exponential decay. As we increase both alpha and beta, we tend to shift this distribution more to the right. We also tend to see more of a curve in the distribution, rather than just a dropping or leveling off. So let's compare the PDF for the gamma distribution to the PDF for the exponential distribution and see if there actually is something to this relationship. So here's the exponential PDF. The exponential distribution is 1 over beta times e to the negative y over beta. The gamma distribution looks like this. The gamma distribution is 1 over the gamma function evaluated at alpha times beta raised to the alpha times y to the alpha minus 1 times e to the negative y over beta. So on first glance, the gamma function is quite a bit more complicated. But what happens to this gamma function if we let alpha, say, be equal to 1? Well, if alpha is equal to 1, then right away we notice that this y term here is going to drop out of the gamma distribution, or the gamma function. The gamma function evaluated at 1 is 1 minus 1 factorial, or 0 factorial, which is 1, so that drops out. Beta raised to the first power is just beta itself. So if we plug in 1 for this alpha parameter, we get an exponential distribution. Or excuse me, if we plug in, that is a typo. That alpha should be 1, not 2. Apologies for that. So our exponential distribution is just a gamma with alpha equal to 1. Now, we have a lot of fun results with this gamma function. Here's one of the first. So let E1, E2, all the way through En be IID, independent, identically distributed sequences of exponential random variables with parameter lambda. We'll define a new random variable s, which is the sum of exponentials. Now those exponentials themselves are distributed gamma with alpha equal 1, beta equal beta. But if we add up a bunch of exponentials, we get back a gamma. Specifically, we get back a gamma with parameters and beta. We'll actually prove this result a little bit later. We do need one additional tool in our arsenal in order to do so. So let's talk about some properties of the gamma distribution. So the expected value of the gamma distribution is alpha times beta. The variance of the gamma distribution is alpha times beta squared. So let's let y be equal to alpha beta, or y be a gamma distribution with parameter alpha beta. Let's go ahead and prove this expected value result. We are going to make use of an awesome trick in order to prove this. So let's start by setting up the expected value. So our expected value of a gamma is just y times the PDF integrated over the support with respect to y. Now I'll combine like terms together. Specifically, I'll combine those y's together. Now you may be looking at this integral and thinking, holy cow, we never did anything like this in Calc 2. How the heck are we going to integrate this? Well, we've got a trick. The trick here to integrating this will be to make our integral look like a PDF. Now notice that y raised to the alpha power is really just y raised to the alpha plus 1 power minus 1. So what if I can write everything within this expected value as some constant times a gamma distribution? So let's make it look like another density function. The way I like to begin this is by dragging all of the constants out of my integral. So here I'm dragging out 1 over the gamma function evaluated at alpha times beta raised to the alpha. What I'm going to do next is try to figure out what constants I need to put back into this integral to make this a valid PDF. Well, I want to make this look like a gamma distribution because we have y raised to some power times e raised to the negative y times something. The constants that make this a gamma distribution are these. 1 over the gamma function evaluated at alpha plus 1 times beta raised to the alpha plus 1. Now, in order to multiply by a constant, I need to also divide by this constant. So here I've put the reciprocal of the constant outside the integral. The reason that making this look like a PDF is so advantageous is because this entire integral, the random variable integrated over its support, becomes 1. So right away, that nasty integral form is gone. So we're left with some constants that we need to combine and simplify. So we have 1 over the gamma function evaluated at alpha times beta raised to the alpha times the gamma function evaluated at alpha plus 1 times beta raised to the alpha plus 1. So we'll combine the gamma function terms and the beta terms to get a final result. So simplifying those beta terms is a little bit easier at first because we've got beta raised to the alpha plus 1 divided by beta raised to the alpha, so just a single beta is left. In order to simplify those gamma functions, we'll take advantage of the recursive relationship between gamma functions. Specifically, we learned previously that the gamma function evaluated at alpha plus 1 is the same as alpha times the gamma function evaluated at alpha. So now our gamma functions cancel, our extra betas cancel, and we get alpha beta for the expected value. Pretty cool. So let's take a look at an example. We are looking at 4-week summer rainfall totals in a Midwestern state. We're assuming that these follow a gamma distribution with alpha 1.6, beta equal to 2. Let's find the mean and variance of the 4-week rainfall totals. So our mean, or our expected value, E of y, is alpha times beta, so 1.6 times 2, or 3.2 for our expected summer rainfall. Our variance is alpha times beta squared, so 1.6 times 2 squared, or 6.4 inches over 4 weeks. In order to find the probability that the 4-week rainfall total exceeds 4 inches, we don't want to try to integrate that PDF unless we absolutely have to. So here we'll use an R function to help us out. Specifically, we'll use the gamma suffix to indicate our gamma function, P to indicate that we want probability up to a particular point. Our parameters in the gamma distribution are represented by shape and scale arguments in R. The shape parameter represents alpha, the scale parameter represents beta. So the probability of observing up to 4 inches of rainfall over a 4-week period is 71%, 0.71. The probability of exceeding 4 inches will then be the complement, 1 minus 0.71 or 29%. Let's take a look at another example. Annual incomes for heads of household in some city have an approximate gamma distribution with alpha equal 50, beta equal 1,000. Let's find the mean and variance of income. Would we expect to find many incomes in this city over $70,000? So will that Y be a gamma distribution? Let's find the expected annual head of household income. We get alpha times beta, or we expect the head of household in this city to earn about $50,000 per year. The variance of income, as you probably know, is quite large, both in practice and with this gamma distribution. We get a variance of $50 million. If we want to find the probability that a person in this particular hypothetical city earns more than $70,000 per year, we'll take 1 minus the cumulative probability up to 70,000. Alpha is 50, beta is 1,000, so a very small probability, about 0.5%. Now let's take a look at another special case of the gamma distribution, the chi-squared distribution. The chi-squared distribution is going to become very useful to us later in the semester when we start thinking about random samples from some distribution. It turns out now that it's actually just a special form of the gamma. So we say that Y follows a chi-square distribution with parameter nu if we can write it as a gamma distribution with nu over 2 for alpha and beta equal 2. This kind of curly V looking symbol is actually a lowercase Greek letter nu. So let's find the expected value and variance for this distribution and write the PDF of Y. So starting with the expected value of the chi-square distribution, the expected value is alpha times beta, so nu over 2 times 2, or nu. The variance of a chi-square distribution is alpha times beta squared, so nu over 2 times 2 squared, or 2 nu. The chi-square distribution PDF then looks like this, plugging in a nu over 2 everywhere we see alpha, 2 everywhere we see beta. So we get this distribution. Again, the chi-square distribution will become very useful to us later on when we start thinking about random samples. So let's take a look at one more example. Suppose that a random variable y has the following PDF. Y is distributed according to the PDF k times y raised to the 3 times e raised to the negative y over 2. So what value of k makes f of y a valid PDF? Well, we could integrate this entire PDF over its support and solve for y numerically, but recognizing a PDF is incredibly useful, not just when we're working with the gamma distribution. So we want to start recognizing certain forms of distributions. A PDF that looks like this, y raised to something times e to the negative y something, is usually a gamma distribution. So looking at this PDF compared to our definition of a gamma gives us that this is going to be a gamma with alpha equal to 4. I'll let you figure out beta on your own. In the next video, we will take a look at one more continuous distribution, the beta distribution. I'll see you then.